Elimination reactions happen with alkyl leaving group. The leaving group is either a halogen or a better leaving group like the OTS or the OMS. Now, the alkyl leaving group is going to react with a base. There are two types of bases in there. We have a strong base and we have a weak base. And we have two types of solvents. We have polar protic or aprotic solvent. And those types of bases and solvents, together with the type of the alkyl halide, will determine in what mechanism the reaction is going to go. There are two mechanisms like SN1 and SN2. There are two mechanisms for elimination, E1 and E2. Now, if elimination happens with substitution, then the ones happen together and the twos happen together. You cannot have E1 and SN2 in the same reaction because the mechanism is different. As a reminder, SN1 goes with carbocation intermediate. So this is why you need E1 with it, because E1 also goes with a carbocation intermediate. SN2 is a one step, so if E2 happens with it, then I'm expecting that E2 is going to be a one step also. Now, with respect to the general reaction, when we say elimination, this means that the product is an alkene. When you have an alkene as a product, there might be a possibility you have stereoisomers. You have the cis and the trans. Now, the base here is going to come and take the beta hydrogen. When you're looking at the alkyl halide has an alpha leaving group. So that carbon that is connected to the leaving group, we call it an alpha carbon. And the leaving group is called an alpha leaving group because it's connected to the alpha carbon. Next to that alpha carbon, normally, which is adjacent to the alpha carbon, we have beta carbons. Now, on these beta carbons, we have beta hydrogens. These beta hydrogens are considered somehow acidic hydrogens because of inductive effect. The leaving group is electronegative, so the leaving group is going to take electrons away from this hydrogen and make it partial positive. Okay, so this is the direction of polarization in here, and it's pulling electrons through the sigma bond, making the hydrogen partial positive. The base, we know that bases are nucleophiles, except with a bulky bases. This base over here is going to come and take the beta hydrogen instead of adding to the alpha carbon like what we did in substitution. In substitution, the base was a nucleophile and it added to the alpha carbon to kick out the leaving group. In elimination, the base is a base, and the role of the base is to come and take the alpha hydrogen, form a double bond, and the leaving group is going to leave. Whether the reaction happens in one step, like I just drew, or in two steps in there, that is going to determine the mechanism of the reaction. Now, heat is a must for this reaction to happen because elimination always is present in presence of heat. And when we say heat, we mean more than room temperature, so more than 25 degrees Celsius. There are two types of bases. There are small bases and bulky bases. So this is going to be the small bases over there. So these, we call them all small bases. And then we have here bulky bases. Now, small bases can either be strong or they can be weak. So they can be either strong or weak in this case. And we know that the difference between the nucleophile and the base is the role, because both they contain lone pairs. So if you're talking about nucleophiles, they have lone pairs. And if you look at the base also have lone pairs. So we can easily say that all bases are nucleophiles, except bulky bases, because bulky bases, like for example, potassium tertiary butoxide, lithium diisopropylamide, we've talked about those in SN1 reactions. So this one over here, it's called potassium tertiary butoxide, and this one is lithium diisopropylamide. We've considered these bases also whenever we were talking in chapter 2 about the types of bases. These are bulky bases. They cannot act as a nucleophile because the role of the nucleophile is to add to the sp3 hybrid carbon. And those are too bulky to add to the sp3 hybrid carbon. Always in nucleophiles with SN1 and SN2, they come and they add to the sp3 hybrid carbon, which is basically this carbon over here. This is the sp3 hybrid carbon. But if they are bulky, they will not reach the sp3 hybrid carbon, especially if there are substituents around. So this is why if you have bulky bases always prefer to go by elimination. So they come and they grab the beta hydrogen and form a double bond, and the leaving group leaves. We have those small bases in there, and the small bases are different types. They can be either strong or they can be weak. The strong bases are listed and the weak bases are listed in there. Now we have in between poor bases, but these poor bases, they act as strong nucleophiles. This table comes in handy whenever you are working with reactions, because if you have a reagent in there that is a strong nucleophile, let's say OH, this one is a strong nucleophile and a strong base, I know that the reaction is going to proceed by both SN2 and E2. Then E2 is going to be major. On the other hand, if I have any of those nucleophiles, these are nucleophiles, these are not bases. Now notice the sulfur nucleophiles. We keep saying that strong nucleophiles are negative charge nucleophiles and strong bases are negative charge bases. That's true, with the exception of sulfur. Sulfur acts as a very good nucleophile and it is a very poor base. So whenever it's present, those two are neutral. They are different than the oxygen bases. So whenever those two are present, those two nucleophiles are present, they're going to be strong nucleophiles and they're going to favor only the substitution. Together with all of these nucleophiles, because those nucleophiles are poor bases, they cannot do elimination. With weak bases, we can have both SN1 and E1. Normally, SN1 and E1 happen together unless you have heat. If you have heat, there will be no substitution. It's just elimination, and elimination is going to be the major product. With respect to the bulky bases, under all circumstances, bulky bases, they're going to only favor the E2 elimination. E2 mechanism works with strong bases. And the bases that E2 works with are small bases, small strong bases, and bulky bases. So if we look at the table in there, you need a small strong base. So these are the small strong bases where E2 happens, and you need the bulky bases as well. As with respect to the alkyl halide, tertiary alkyl halide is the fastest. It reacts faster than secondary than primary alkyl halide. And this is where E2 parts from SN2 reaction. Remember, SN2 does not happen with tertiary alkyl halide, but E2 happens with any base. So it works with any base, bulky or small strong bases. Same thing for secondary alkyl halide. But if you wish to carry E2 with primary alkyl halide, you just need bulky base. You cannot carry it with a small strong base. So any of those bases that you see in here, those will not work with E2 elimination if the substrate that you start with is a primary alkyl halide. The solvent that we are using is similar to the SN2 reaction, so it's a polar aprotic solvent. With E2 in particular, we can use polar protic solvent. So we can use polar protic solvent as well. However, the rate of the reaction is going to decrease a little bit, but the reaction is going to happen, but it will take some time in order to finish. The reaction always with E2, it needs heat to proceed, and the heat is above room temperature. As for the stereochemistry of the elimination E2, for elimination to happen, the hydrogen and the leaving group. So let's scroll up here. The hydrogen and the leaving group, normally they need to be in opposite planes. We call these anti-periplanar. They have to be in opposite planes. If you have a stereochemistry in your substrate, then they need to be trains with respect to each other. And if they belong to a cyclohexane, they need to be trains diaxial with respect to each other for elimination to happen. Because the base is going to come and attack the hydrogen. The hydrogen needs to be in a different plane than the leaving group because the leaving group has lone pairs around it. So the base cannot come from the same side as the leaving group because both have lone pairs. They're going to repel each other. So this is why the hydrogen needs to be taken by the base in a different plane, form a double bond, and the leaving group needs to leave. So as a summary, whenever you want to use bulky bases works with all types of alkyl halides. And bulky bases, they only proceed by E2 elimination. Now, for small bases in there, you have to pay attention that the reaction will never happen with primary alkyl halide. So with primary alkyl halide, you'll never have an E2 mechanism if you are working with a small bases. You need a bulky one. However, if you're working with a secondary or tertiary, you can have E2 elimination. Pay attention that tertiary alkyl halides, they don't proceed by SN2, they only proceed by E2. When we carry an elimination reaction, our product is an alkene. And alkenes are classified into monosubstituted, di, tri, and tetra-substituted. And we can arrange those based on stability. So let's highlight the alkene functional group in there. Okay, and then look at the carbons that are connected to the alkene. So if you have one carbon connected to the alkene, this is called a monosubstituted alkene. If you have two R groups that are connected to the alkene, this is called a disubstituted alkene. Disubstituted alkene can either have their substituents either on the same side, and this is going to be the cis isomer, or they can have their substituents on opposite sides, and that is going to be the trans isomer. When we talked about cis and the trans, we said that cis and trans exist in a cycle, and they also exist in a double bond. So here there is no rotation between the cis and the trans. To go from cis to trans, you have to break the pi bond in there. In disubstituted alkene, whenever you have one isomer, you have the other. So if your product is a disubstituted alkene, please draw both the cis and the trans. Always the more stable is the trans because the R groups are in different, they are in different orientation with respect to each other, and they are in different planes. Then we have the tri-substituted alkenes and the tetra-substituted alkenes. The tri-substituted alkenes have 3 carbons around the double bond, and the tetra-substituted has 4 carbons around the double bond. If we want to arrange those based on stability, then the tetra-substituted is going to be the most stable type of an alkene compared to the tri-substituted, compared to the di, compared to the mono. The reason why is because you do have your CH3s. So let's assume that these are carbons in there, and they are the simplest types of carbons, which are CH3s in there. So here I have 4 carbons around the alkene versus 3 carbons around the alkene versus 2 carbons versus 1 carbon. Now, each of these carbons in there is an sp3 hybridization that is connected to an sp2 hybridization. And we know that the sp2 hybridization is more electronegative than the sp3. So the sp2 is going to pull electrons away from the sp3, making the sp3 an electron donating group. And that electron donating group is going to be through inductive effect. We explained inductive effect before, and we said inductive effect is the pull of electrons through the sigma bond, and that is formed due to the difference in the electronegativity between the atoms that are that constitute that sigma bond. Here we have an sp3 hybrid carbon and an sp2 hybrid carbon in there. So we said here that the sp3 carbon is an electron donating group in there. The more electron donating group, the better in this case. So this is why here we have 4 electron donating groups. They are giving electrons to the double bond, which makes this structure here more stable. And the more stable the structure is, the higher percentage it exists. So this is why whenever you have a higher degree of substitution of alkene that you might form, that is going to be the most stable product. And we're going to call this the Zaitsev product. So the Zaitsev product is the most substituted alkene that you can form.